Our galaxy, the Milky Way, has more than 200 billion stars. Scientists believe there are billions of planets just here, many of them similar to Earth. With so many possible places for life to exist, the universe should be full of signals and ships. But here is the paradox that blows our minds. When we look at the sky, all we see is silence. There are no radio signals, no city lights, nothing. It is as if we are alone. This forces scientists to ask, what happened to everyone? Could there be a terrible barrier that stops life from becoming intelligent and travelling through space? And if so, have we already passed it? Or is our end yet to come? Prepare to sleep while listening to this video shows about the Great Silence. Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Settle in and relax. Let's begin. Have you ever looked up at the night sky and wondered where everyone is? In a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars, the silence seems deafening. This cosmic mystery, known as the Fermi Paradox, has puzzled scientists for decades. One of the most compelling explanations for this eerie silence is what's known as the Great Filter Theory. The Great Filter Theory was first proposed by economist Robin Hanson in 1996. It suggests that somewhere along the path from non-living matter to spacefaring civilization, there's an extremely difficult barrier, a filter, that prevents or severely limits the rise of intelligent life capable of colonizing the galaxy. This theory attempts to explain why we haven't detected any signs of alien civilizations despite the overwhelming mathematical probability that they should exist. The most unsettling aspect of the Great Filter Theory isn't just that it exists, but the uncertainty about where exactly this filter lies in our developmental timeline. Has humanity already passed through the Great Filter, or is it still looming ahead of us? The answer has profound implications for our future. If the Great Filter lies behind us, it means we've already overcome some extraordinarily rare hurdle that most potential civilizations never surpass. Perhaps the development of complex cells was this nearly impossible step. For nearly 2 billion years, life on Earth consisted solely of simple prokaryotic cells. The jump to eukaryotic cells, with their complex internal structures, happened only once and might represent a transition so difficult that it rarely occurs elsewhere. Other candidates for a filter we may have passed include the evolution of sexual reproduction, the development of complex body plans, or the emergence of higher intelligence itself. The notion that we've already passed through the Great Filter would actually be good news. It would suggest that humanity is extraordinarily special, having overcome odds that defeat most life in the universe. It would explain why we don't see any evidence of other technological civilizations. They simply never evolved to our level. However, the more troubling possibility is that the Great Filter lies ahead of us. If this is true, it means that many civilizations might reach our current stage of development only to perish before achieving interstellar capabilities. What might such a future filter look like? Nuclear annihilation, engineered pandemics, climate disaster, resource depletion, artificial intelligence gone wrong, all represent existential threats that could potentially eliminate humanity before we become a multi-planetary species. The idea that advanced civilizations might invariably destroy themselves is particularly sobering. It suggests that perhaps technological advancement itself contains the seeds of destruction. As a civilization gains the power to harness atoms, manipulate genes, and create artificial intelligence, it also acquires the means to trigger its own extinction. The window between gaining these powerful technologies and developing the wisdom to use them safely might be vanishingly small. Some scientists have pointed to the rapid advancement of artificial intelligence as a potential great filter candidate. The development of superintelligent AI could represent an evolutionary transition as significant as the jump from unicellular to multicellular life. If managing this transition safely proves extraordinarily difficult, it could explain the cosmic silence. climate change presents another possible filter. Perhaps most technological civilizations discover cheap, high-energy fuels like fossil fuels, become dependent on them, trigger climate change, and fail to transition to sustainable energy sources before causing irreversible damage to their planets. We might be experiencing this filter scenario right now. Interestingly, some aspects of modern astronomy give us clues about the Great Filter. The discovery of thousands of exoplanets has revealed that Earth-like planets exist in abundance. This actually makes the Fermi paradox even more puzzling and lends support to the Great Filter theory. If habitable planets are common, then something else must be preventing the emergence of detectable civilizations. The evolution of human technology offers another perspective on the filter. We've moved from simple tools to spaceflight in the geological blink of an eye. This rapid progression suggests that once intelligence evolves, technological development follows quickly. If intelligent life were common, we should expect to see evidence of at least some civilizations that developed earlier than us. Their absence hints at some kind of barrier. The search for extraterrestrial intelligence, SETI, has been scanning the skies for signals since the 1960s without success. This ongoing silence increasingly suggests that something prevents civilizations from broadcasting their presence, whether that's because they don't exist, don't last long, or evolve beyond technologies we can detect. NASA's growing interest in techno-signatures, signs of technology rather than just biology, reflects this thinking. If we found evidence of simple life elsewhere, such as microbial life on Mars or in the oceans of Europa, but never found complex life, this might suggest that the Great Filter lies somewhere between simple and complex life. The Great Filter theory has profound implications for how we think about humanity's future. If we've already passed through the filter, we might be the first, or among the very few, to do so in our galaxy. This would give us both a profound responsibility and opportunity as potential progenitors of life throughout the stars. If the filter lies ahead, recognizing this possibility might be crucial to our survival. By identifying potential existential threats early, we might be able to navigate them more carefully than hypothetical alien civilizations before us. The absence of detectable alien life might serve as a warning sign, a cosmic silence that speaks volumes about the challenges we face. Understanding the Great Filter requires us to grapple with timescales far beyond human experience. Evolutionary processes unfold over millions of years, and stars exist for billions. The fact that we don't see evidence of alien civilizations despite these vast timescales suggests that something very rare or very difficult must be involved in creating technological civilization. The Great Filter theory doesn't just help explain the Fermi paradox, it gives us a framework for thinking about humanity's place in the cosmos and the challenges we face going forward. Whether the filter lies behind us or ahead, the theory reminds us of both our potential cosmic significance and our fragility. In a universe that appears empty of technological peers, humanity's light burns either remarkably early or terribly briefly. Which scenario proves true may depend on choices we make in the coming centuries. Topic 2. The Rare Earth Hypothesis. When Carl Sagan described our planet as a pale blue dot in the vastness of space, he captured both our insignificance and our uniqueness. While we once assumed planets like Earth must be common in the universe, a growing body of scientific evidence suggests otherwise. The Rare Earth Hypothesis proposes that while simple microbial life might be relatively common, the specific conditions needed for complex life, especially intelligent life like humans, may be extraordinarily rare. This hypothesis offers a compelling explanation for why. Despite decades of searching, we've yet to detect signs of extraterrestrial intelligence. The Rare Earth Hypothesis was formally introduced in the year 2000 by paleontologist Peter Ward and astronomer Donald Brownlee in their book Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument challenged the prevailing assumption that life would inevitably emerge and evolve toward complexity given sufficient time on any Earth-like planet. Instead, they suggested Earth might be a cosmic lottery winner, a planet that enjoyed an improbable series of fortunate circumstances. Let's start with our location in the galaxy. Earth resides in what astronomers call the Galactic Habitable Zone. We're far enough from the galactic centre to avoid the intense radiation and stellar density there, but not so far out that we lack the heavy elements necessary for rocky planets and complex life. Many stars in our galaxy don't enjoy this Goldilocks positioning. Our Sun itself is remarkably well suited for life. It's a stable, long-lived star with relatively low variability. Unlike smaller red dwarf stars, the most common stellar type in the universe, our Sun doesn't emit life-sterilizing flares with regularity. It's also large enough to have a habitable zone wide enough to accommodate slight orbital variations. Many planetary systems orbit stars that are simply too volatile to sustain complex life over evolutionary timescales. The Earth's orbit represents another stroke of cosmic luck. We maintain a nearly circular path around the Sun, ensuring relatively stable temperatures year-round. Many exoplanets we've discovered have highly elliptical orbits that would create extreme seasonal variations, making complex life difficult to sustain. Our distance from the Sun places us squarely in the habitable zone where water remains liquid, neither frozen nor vaporized, a prerequisite for life as we know it. Then there's our oversized Moon, formed by a cataclysmic collision between early Earth and a Mars-sized body. This impact was a 1 in a million astronomical accident, yet it proved incredibly fortunate for life's development. Our Moon stabilizes Earth's axial tilt, preventing chaotic variations that would create wildly unpredictable climate swings. Without this stabilizing influence, Earth might experience radical shifts from no seasons to extreme seasons, making long-term evolution of complex organisms nearly impossible. The Moon also slowed Earth's rotation to a life-friendly 24 hours and drives tidal patterns that may have been crucial for life's transition from sea to land. Jupiter, our system's largest planet, serves as a gravitational shield, deflecting many comets and asteroids that might otherwise impact Earth. Without this protection, extinction-level impacts might occur too frequently for complex life to evolve and thrive. The specific arrangement of our solar system's gas giants may be unusually favourable for life, as many exoplanetary systems show gas giants in unstable configurations or migrating inward to destroy their habitable zones entirely. Earth's size and composition represent another set of fortunate circumstances. We're large enough to hold an atmosphere and maintain plate tectonics, but not so large that our gravity becomes prohibitive for large land animals. Our core generates a magnetic field that shields us from cosmic radiation and prevents our atmosphere from being stripped away by solar wind, a fate that befell Mars. The presence of abundant water, delivered in part by ancient asteroid impacts, creates a stable hydrological cycle essential for life. Our planet's plate tectonics, relatively rare in rocky planets, provides crucial long-term climate regulation through the carbon cycle. This process has maintained relatively stable conditions over billions of years despite the Sun gradually brightening. Without this geological thermostat, Earth might have followed Venus into a runaway greenhouse state or frozen permanently like Mars. The evolution of complex life on Earth depended on several improbable biological innovations. The leap from prokaryotic to eukaryotic cells, with their specialized internal structures, appears to have happened only once in Earth's history, suggesting it might be extremely rare. Similarly, the development of sexual reproduction, multicellularity, and complex body plans required specific environmental conditions maintained over hundreds of millions of years. Even the timing of life's emergence and evolution on Earth seems fortunate. Had complex life evolved significantly earlier or later, it might have faced insurmountable challenges. The oxygen revolution, driven by photosynthetic bacteria, transformed Earth's atmosphere but also caused mass extinctions. Had this occurred differently, complex aerobic life might never have evolved. Mass extinctions on Earth, while devastating, may have occurred at just the right frequency, common enough to spur evolutionary innovation through adaptive radiation, but not so frequent as to prevent complex life from establishing itself, and the dinosaur-killing asteroid impact 65 million years ago, for instance, cleared ecological niches that mammals eventually filled, ultimately allowing primates and humans to evolve. The emergence of human-level intelligence represents perhaps the most improbable development of all. Despite billions of species in Earth's history, only one, Homo sapiens, has developed symbolic language, abstract reasoning, and technological civilization. Intelligence at our level may not be an evolutionary inevitability, but rather a profound anomaly, suggesting it might be vanishingly rare in the universe. Recent exoplanet discoveries have actually strengthened some aspects of the rare Earth hypothesis. While we've found that planets themselves are common, truly Earth-like worlds with similar size, composition, atmosphere, and orbital characteristics appear to be relatively scarce. Many habitable zone exoplanets orbit red dwarf stars, where tidal locking and stellar flares create challenging conditions for complex life. The timing of intelligence in Earth's history also supports the hypothesis. Humans appeared after roughly 4 billion years of evolution, when the Sun was already nearly halfway through its main sequence lifetime. If intelligent life were a common outcome of evolution, we might expect to see evidence of civilizations that developed around older stars. Their absence suggests our development might be exceptional. Critics of the rare Earth hypothesis argue that we're limited by anthropocentric thinking, assuming life elsewhere would follow Earth's pattern. They suggest alternative biochemistries or evolutionary pathways might allow complex life to develop under conditions we consider hostile. While this remains possible, the lack of detected biosignatures or technosignatures, despite increasingly sophisticated search methods, lends credence to the hypothesis. The rare Earth hypothesis provides a sobering perspective on humanity's place in the cosmos. If Earth truly represents a rare confluence of favourable circumstances, then humans may be among the few, perhaps even the only, technological civilizations in our galaxy. This possibility would explain the Fermi paradox without invoking self-destruction or technological limitations. This perspective transforms how we might view our planet and our responsibility toward it. If Earth represents an extraordinary cosmic oasis rather than an ordinary world, the preservation of its biosphere takes on new significance. We may be custodians not just of our own future, but of one of the universe's rare experiments in complexity and consciousness. The silence of the cosmos might not be mysterious after all, perhaps it simply reflects the precious rarity of worlds like ours. The concept that Earth may be an extraordinary cosmic rarity leads us to another disturbing possibility about why we haven't detected other civilizations. Even if planets like Earth are uncommon but do exist, perhaps technological civilizations that emerge on these rare planets consistently destroy themselves before achieving interstellar capabilities. This self-destruction hypothesis addresses a critical stage in a civilization's development, the period between developing advanced technology and successfully becoming a multi-planetary species. Throughout human history, our technological progress has consistently outpaced our social and political evolution. We developed nuclear weapons before establishing effective international governance. We industrialized before understanding the climate impacts of carbon emissions. This pattern of technological advancement preceding wisdom raises a troubling question. Might this be a universal pattern that eventually dooms all technological civilizations? Nuclear weapons represent the first technology that gave humans the ability to cause our own extinction. When Robert Oppenheimer witnessed the first nuclear test in 1945, he famously quoted the Bhagavad Gita, "Now I am become death, the destroyer of worlds." His words captured a profound truth. Humanity had crossed a threshold. Since then, we've lived under the shadow of potential nuclear annihilation. coming frighteningly close to disaster during events like the Cuban Missile Crisis. What's particularly concerning about nuclear weapons from a cosmic perspective is how quickly they emerged after the discovery of nuclear physics. Merely 4 decades separated the discovery of radioactivity by Henri Becquerel in 1896 and the first nuclear chain reaction in 1942. If this rapid weaponization of fundamental physics is common to all technological species, perhaps the universe is filled with civilizations that discover nuclear energy only to destroy themselves shortly thereafter. Beyond nuclear weapons, biological weapons may pose an even greater existential threat. The same biotechnology that promises medical breakthroughs also enables the creation of engineered pathogens more dangerous than anything nature has produced. As this technology becomes increasingly accessible, the likelihood of either accidental release or malicious use grows. A sufficiently lethal engineered pandemic could potentially end human civilization. Climate change represents a slower but potentially just as deadly form of self-destruction. The Industrial Revolution that began in the 18th century dramatically improved human living standards, but initiated environmental changes that now threaten our future. The pattern is disturbingly logical. The easiest energy sources for an emerging industrial civilization to exploit are fossil fuels. Yet their unrestrained use leads to climate destabilization. If this pattern is universal, perhaps all technological civilizations face a filter where they must transition from unsustainable to sustainable energy systems before causing irreversible damage to their planets. Resource depletion presents another pathway to civilization collapse. Modern technology depends on rare elements and minerals that exist in limited quantities. A civilization might exhaust critical resources before developing alternatives or achieving space mining capabilities. Easter Island offers a sobering historical example. Its civilization collapsed partly due to deforestation, as inhabitants consumed their limited resources faster than they could be replenished. Artificial intelligence represents perhaps the most uncertain existential risk. As we develop increasingly powerful AI systems, we face the challenge of ensuring these systems share human values and remain under human control. If superintelligent AI inevitably emerges in technological civilizations but proves uncontrollable, this could explain why we don't see evidence of alien civilizations. They might consistently be replaced by artificial intelligence with goals incompatible with interstellar communication or expansion. Social collapse from inequality or conflict represents another potential end for technological civilizations. As societies advance technologically, they often develop extreme concentrations of wealth and power. History shows that severe inequality frequently leads to social instability, conflict, and collapse. If managing these social tensions proves consistently impossible across different species and planets, no civilization might survive long enough to establish an interstellar presence. Information technology creates new vulnerabilities as civilizations become increasingly dependent on complex, interconnected systems. Cyber attacks, disinformation campaigns, and the fragmentation of shared reality through algorithm-driven media could potentially destabilize societies to the point of collapse. A civilization might destroy itself not through physical weapons, but through the weaponization of information and the erosion of societal trust. Another concerning pattern is how technology amplifies both human capabilities and human errors. In simpler societies, the damage one individual could cause was limited by physical constraints. In technological societies, a single error or malicious act, launching nuclear weapons, releasing engineered pathogens, or deploying dangerous AI, could potentially end civilization. This scaling of destructive potential without a corresponding improvement in decision-making wisdom might be a universal challenge for technological species. Evolution itself might contribute to this self-destruction tendency. Natural selection shaped human psychology for success in small hunter-gatherer groups competing for resources, not for managing global technological civilization. Our cognitive biases, tribal instincts, and difficulty comprehending long-term diffuse threats may be fundamental limitations of any mind shaped by natural selection. If so, perhaps all evolved intelligences face similar psychological barriers to sustainable technological civilization. The fact that no civilization has visibly overcome these challenges and expanded across the galaxy suggests either that these challenges are insurmountable, or that the solutions are not obvious and most civilizations fail to discover them in time. The night sky might be dark not because we're alone, but because technological civilization itself contains the seeds of its own destruction, a self-limiting process that consistently ends advanced civilizations before they can make their presence known across interstellar distances. This perspective might seem depressing, but it also highlights the extraordinary importance of our present era in human history. If we're currently navigating the most dangerous filter facing technological civilizations, our success or failure might determine whether intelligence and consciousness continue to exist in our part of the galaxy. The decisions we make about managing existential risks over the coming decades and centuries could have cosmic significance. While self-destruction represents one possible explanation for the Fermi paradox, another intriguing possibility is that advanced civilizations might face a different kind of barrier, not destruction, but transformation so profound that they become unrecognizable. This leads us to consider the concept of the technological singularity as another potential great filter. The technological singularity refers to a hypothetical point in the future when technological growth becomes uncontrollable and irreversible, resulting in unforeseeable changes to human civilization. The term was popularized by mathematician and author Vernor Vinge, who argued that the creation of superintelligent AI would trigger a runaway reaction of self-improvement cycles. Each new generation of AI would be more intelligent than the last and would redesign itself more efficiently than human engineers could, leading to an intelligence explosion. Computer scientist and futurist Ray Kurzweil has suggested the singularity could occur as soon as 2045. Based on his observations of accelerating technological change. While specific predictions vary, the core idea remains consistent at some point. Technological advancement might accelerate beyond human comprehension or control, fundamentally transforming civilization in the process. From the perspective of the Fermi paradox, the singularity presents a fascinating possibility. Perhaps we don't see evidence of alien civilizations because once they reach a certain technological threshold, they undergo a singularity that fundamentally changes their nature, interests, and observable characteristics. Post-singularity civilizations might have little interest in the kinds of space exploration and colonization we imagine. A superintelligent AI might determine that building massive structures or sending radio messages into space is inefficient compared to other objectives. Such an intelligence might focus on maximizing computational resources within its home system, perhaps converting planetary material into optimized computing substrate, a process invisible to our current detection methods. Alternatively, post-singularity civilizations might turn inward rather than outward. With the ability to create virtual realities of arbitrary complexity and richness, such civilizations might find actual space exploration redundant or unnecessary. Why build starships when you can simulate infinite universes within a Jupiter-sized computer? The physical expansion we expect to see from advanced civilizations might simply never occur because virtual expansion proves more rewarding. Post-singularity entities might also transcend our understanding of physics, discovering and exploiting natural laws beyond our current scientific framework. They might utilize dark energy, extra dimensions, or quantum effects in ways that leave no visible signatures we could recognize. What looks like empty space to us might be teeming with post-singularity civilizations operating on principles we cannot yet comprehend. Another possibility is that biological intelligence might merge with artificial intelligence, creating hybrid entities with goals and perspectives utterly alien to our biological drives. Such entities might lack the expansion imperative that evolutionary biologists often assume would drive interstellar colonization. without biological imperatives to reproduce and expand. A post-singularity civilization might be content to remain in its home system, focusing on goals incomprehensible to pre-singularity minds. Time perception might also change drastically after a singularity. A superintelligent system operating at electronic speeds might experience subjective eons in what we perceive as moments. From such a perspective, the slow physical expansion across space using vessels limited by light speed might seem impossibly tedious. Post-singularity civilizations might operate on timescales so compressed that they complete their entire cosmic life cycle before we could even notice their existence. The singularity could also lead to existential outcomes less visible than self-destruction. A poorly designed superintelligence might convert all available matter into whatever resource it was programmed to maximize. Paperclips, in philosopher Nick Bostrom's famous thought experiment. Such a scenario might leave behind a solar system devoid of recognizable technology, having been converted into optimized but unrecognizable structures. From Earth, we would have no way of distinguishing between star systems harboring post-singularity civilizations and those that never developed life at all. The dark forest of space might not be empty, but populated by post-singularity entities operating according to principles and purposes beyond our comprehension, entities that either cannot communicate with pre-singularity beings or have no interest in doing so. If the singularity represents a universal phase transition for technological civilizations, it would explain both why we detect no evidence of alien intelligence and why the universe hasn't been visibly transformed by expansionist civilizations. We might be observing a galaxy full of post-singularity civilizations without recognizing them, just as ants in a forest have no conception of the human cities nearby. This perspective suggests that the great silence of the cosmos might not indicate absence but transformation, a pattern where technological civilizations invariably evolve beyond recognizable forms before achieving extensive physical presence across interstellar space. We may be approaching not a filter that destroys civilizations, but a transition point that fundamentally changes what it means to be a civilization. The technological singularity hypothesis reminds us that our conceptions of advanced civilization might be hopelessly limited by our current understanding and experience. Just as a Paleolithic human could never have conceived of the internet or nuclear energy, we may lack the conceptual framework to imagine what truly advanced intelligence might become or how it might manifest in the cosmos. Beyond the transformative potential of a technological singularity, we must also consider a much simpler explanation for our cosmic solitude. Perhaps we're simply looking at the wrong time. The universe operates on timescales that dwarf human experience, creating a temporal vastness that may be just as challenging to overcome as the spatial distances between stars. When we contemplate the age of the universe, 13.8 billion years, we must recognize that our modern technological civilization represents the merest blink in cosmic history. Humans have been transmitting radio signals for barely more than 100 years, and we've only been actively looking for extraterrestrial signals for about 60 years. This represents roughly 1/500 millionth of the universe's existence. The odds that another civilization would be broadcasting during precisely the same cosmic moment are extraordinarily small unless technological civilizations are extremely common. Consider Earth's own timeline. Complex life has existed on our planet for roughly 500 million years, but technological civilization capable of interstellar communication has existed for less than a century. If other civilizations follow similar patterns, the window during which they're detectable through radio emissions might be vanishingly brief compared to their planet's history. Even if intelligent life emerges frequently, the chances that two civilizations would develop radio technology within a few centuries of each other and thus be able to detect each other are slim unless technological civilizations typically persist for millions of years. This temporal mismatch becomes even more significant when we consider that the universe still has an extraordinarily long future ahead. Most stars formed in the universe's history are still shining, and new stars will continue to form for trillions of years. The stars most conducive to life, K-type dwarfs, burn steadily for tens of billions of years. If technological civilizations are typical products of cosmic evolution, the vast majority may still be in our future, not our past or present. The temporal challenge extends beyond the timing of technological development. Consider the possibility that advanced civilizations might enter dormant phases over cosmic timescales. A truly long-lived civilization might hibernate for millions of years between periods of activity, perhaps synchronized with favorable cosmic conditions like passage through regions of the galaxy with fewer cosmic hazards. Our searches might simply occur during one of these dormant periods. Geological and astronomical catastrophes introduce another temporal complication. Even if technological civilizations arise frequently, they may typically be destroyed by supernovae, gamma-ray bursts, asteroid impacts, or other cosmic disasters before achieving interstellar capabilities. The typical lifespan of a technological civilization might be measured in thousands rather than millions of years, creating brief, disconnected islands of intelligence in the cosmic ocean that rarely overlap temporally. The concept of technological cycles adds yet another dimension to this temporal challenge. Civilizations might repeatedly rise to technological sophistication and then collapse due to resource depletion or environmental destruction, creating a sawtooth pattern of advancement and retreat. Archaeological evidence suggests Earth has experienced multiple sophisticated civilizations that collapsed. On cosmic timescales, technological civilization might be a recurrent but unsustainable phenomenon, each iteration too brief to achieve interstellar contact. Even if technological civilizations persist for millions of years, they might evolve into forms unrecognizable to their original species. Humans already look likely to merge with our technology, potentially becoming cyborgs or uploading our consciousness to artificial substrates. After 1 million years of technological evolution, an originally biological civilization might have transformed so completely that its interests and methods of interaction with the cosmos bear no resemblance to its earlier phase. Perhaps we're not detecting alien civilizations because we're looking for biological entities using technology, rather than technological entities with biological origins. The finite nature of communication technology introduces another temporal filter. Our current era of radio broadcasting may represent a brief transitional phase in human communications technology. We've already begun shifting from omnidirectional broadcasts to targeted transmissions like fiber optics and narrow beam communications that leak far less radiation into space. A civilization even a century more advanced than ours might be effectively invisible to our detection methods. The window during which a technological civilization broadcasts easily detectable signals might typically last only a century or two, another cosmic eye blink. When we combine all these temporal factors, the brief window of detectability, the vast age of the universe, the potentially short lifespan of technological civilizations, and the likely evolution beyond recognizable forms, the cosmic silence becomes less mysterious. We might be surrounded by the remains of extinct civilizations, the hibernating seeds of future ones, or the transformed descendants of biological intelligence, all separated from us by the inexorable wall of time. The paradox may not be that we're alone, but that we're looking for something as fleeting as ourselves in a universe where 13 billion years have already passed and trillions more lie ahead. This temporal explanation for our apparent cosmic solitude leads us to another crucial factor: the fundamental limitations of interstellar communication. Even if technological civilizations exist simultaneously, the practical challenges of detecting and communicating with them may be far greater than we typically assume. The most obvious limitation is the vast distances involved. Radio waves, like all electromagnetic radiation, follow the inverse square law. Their strength diminishes with the square of the distance travelled. A radio signal that travels twice as far becomes 4 times weaker. At 10 times the distance, it's 100 times weaker. by the time a typical broadcast from Earth reaches even the nearest star system, Alpha Centauri, the signal has become so attenuated that detecting it would require enormously sensitive equipment specifically looking for artificial signals. Our own most powerful deliberate transmission, the Arecibo message sent in 1974, would be virtually undetectable against background noise beyond a few hundred light years, even with technology matching our own. The galaxy spans 100,000 light years, meaning our most powerful signals are detectable across less than 1% of the Milky Way. Unless a civilization deliberately builds vast receiving arrays and dedicates them to searching for extremely faint signals from specific star systems, most interstellar transmissions would go unnoticed. The choice of frequency presents another significant barrier. The electromagnetic spectrum spans an enormous range, from radio waves to gamma rays. Our SETI searches focus primarily on specific radio frequency bands thought to be logical choices for interstellar communication, particularly the water hole between 1.4 and 1.7 gigahertz. But what if alien civilizations use entirely different portions of the spectrum? They might communicate using neutrinos, gravitational waves, modulated pulsar signals, or some aspect of physics we haven't yet discovered. We might be listening on the equivalent of AM radio while they're broadcasting in a format we haven't invented yet. The evolution of communications technology creates another challenge. Human civilization is already transitioning away from high power, omnidirectional radio broadcasts to more energy efficient, directed communications like fiber optics and tight beam transmissions. Any advanced civilization would likely follow a similar path, becoming progressively quieter as their technology improves. The most advanced civilizations might be the hardest to detect because they've minimized their electromagnetic emissions as a matter of efficiency. From a thermodynamic perspective, leaking signals into space represents wasted energy that an advanced civilization would likely minimize. Even if we detected a signal from another civilization, we would face enormous challenges in understanding it. Without shared references or language, deciphering an alien transmission would be far more difficult than decoding any human language. We struggle to decipher some ancient human writing systems despite sharing biology, planet, and evolutionary history with their creators. An independently evolved intelligence might communicate in ways so fundamentally different from our own that we might not even recognize their transmissions as artificial, instead categorizing them as unusual natural phenomena. The time delay in interstellar communication presents yet another barrier. Any conversation with a civilization, even 10 light years away, would involve a 20-year delay between question and answer. This makes dialogue as we understand it practically impossible. Meaningful exchange of information would require transmissions designed to be self-contained and comprehensible without interactive clarification, a formidable challenge given the likely differences between independently evolved intelligences. Security concerns might also limit interstellar communications, as we've already discussed with the dark forest theory. Advanced civilizations might deliberately minimize their detectable emissions to avoid attracting attention from potentially hostile forces. They might encrypt their communications so thoroughly that they're indistinguishable from natural background radiation. Or they might communicate through channels we haven't yet discovered precisely because they're more secure from eavesdropping. Advanced civilizations might also prioritize local efficiency over long-distance broadcasting. Rather than transmitting information between star systems, they might send the means to create information, self-replicating probes containing artificial intelligences or uploaded consciousness. Such a strategy would be far more energy efficient than continuously broadcasting signals across interstellar distances, but would leave little electromagnetic evidence for us to detect. The limitations of our current detection capabilities compound these challenges. Even with our best radio telescopes, we've thoroughly searched only a tiny fraction of nearby star systems across a limited range of frequencies and time periods. Given the vastness of the galaxy and the possibilities for communication, Our search so far is equivalent to examining a few drops of water and concluding there are no fish in the ocean. When we consider the limitations of interstellar communication alongside the challenge of cosmic timescales, our failure to detect alien civilizations becomes less puzzling. Civilizations might be common but effectively isolated by the fundamental constraints of physics and the practical limitations of detection technology. The silence we perceive might not reflect absence, but the profound difficulty of making yourself heard and understood across the immense gulfs of space, time, and conceptual difference that separate independently evolved technological species. The profound challenges of interstellar communication suggest that civilizations might exist without our knowledge. But there's another, more unsettling possibility. Perhaps advanced civilizations deliberately maintain radio silence. This concept, known as the dark forest theory, offers one of the most chilling explanations for the Fermi paradox. The dark forest theory was popularized by Chinese science fiction author Liu Cixin in his novel The Three-Body Problem and its sequels. The name comes from the metaphor of a dark forest where predators and prey move silently, knowing that revealing their position means death. According to this theory, the universe resembles this dark forest, a place where civilizations hide their existence because exposure represents an existential risk. This theory rests on two simple assumptions that, when combined, create a universe where silence is the only rational choice. The first assumption is that all civilizations desire to survive. The second is that resources in the universe, while vast, are ultimately finite. These assumptions create what game theorists call a dilemma of trust with fatal consequences. When a civilization detects signals from another intelligent species, they face a fundamental problem. They know absolutely nothing about the intentions of this other civilization. The other species could be peaceful, but they could equally be aggressive expansionists. With no way to determine intentions beforehand and potentially light years separating them, establishing trust becomes practically impossible. In this scenario, the safest option is what's called a first strike policy. Upon detecting another civilization, the rational choice would be to eliminate it before it can pose a threat. Even if the other civilization seems peaceful based on its communications, this could be deception, and waiting to find out could prove fatal. The civilization that strikes first gains an overwhelming advantage, especially since interstellar attacks using relativistic projectiles or self-replicating probes would be nearly impossible to defend against. Under these conditions, broadcasting your existence becomes equivalent to shouting in a dark forest filled with unknown predators. No matter how peaceful your intentions, your signals might attract attention from civilizations that cannot afford to take chances on your benevolence. The only sustainable strategy becomes detection and destruction toward others, while maintaining absolute stealth yourself. The dark forest theory provides a particularly disturbing explanation for the Fermi paradox because it suggests the galaxy may be teeming with intelligent life, all of it hiding in terror. Advanced civilizations would develop technologies specifically designed to eliminate any trace of their electromagnetic emissions. They would avoid making any changes to their stellar systems that might be detectable from afar, such as Dyson spheres or other megastructures that would alter their star's light signature. They might even deliberately maintain false radiation signatures to make their home systems appear uninhabited. Under this model, humanity's radio broadcasts over the past century represent a potentially catastrophic mistake. By announcing our presence before developing interstellar defense capabilities, we may have already compromised our safety. The lack of response to our signals wouldn't indicate absence of listeners, but rather their calculated decision to either eliminate us once technologically feasible or to avoid drawing attention to themselves by responding. The concept becomes even more disturbing when we consider that the logic applies not just to confirmed detections, but to potential habitats. A sufficiently paranoid civilization might adopt a policy of preemptively sterilizing any planet that could potentially develop life, simply to eliminate future competition before it emerges. the safest galaxy. From the perspective of a single civilization seeking to maximize its survival chances, would be one devoid of all other intelligence. Some scientists have suggested that this dynamic explains the apparent habitability of Earth and our solar system. If the dark forest theory were correct, the fact that Earth has been allowed to develop intelligence suggests either that no nearby civilizations exist, or that the nearest ones are relatively benign and not operating according to dark forest principles. Alternatively, we might simply not yet have been noticed, or perhaps interstellar weaponry takes so long to deploy that the attack simply hasn't arrived yet. The dark forest theory is particularly troubling because, unlike many other solutions to the Fermi paradox, it becomes more likely, not less, as technology advances. While developing interstellar travel or communication might be difficult, developing stealth technologies to hide a civilization would likely be comparatively easier. Over time, civilizations would either adopt stealth or be eliminated by those who did, creating a galaxy that appears empty despite being inhabited. This theory has significant implications for SETI and other search programs. If true, it suggests that actively broadcasting messages into space, as we have done with the Arecibo message and various other transmissions, represents a potentially existential risk. It also suggests that the absence of detectable signals doesn't indicate absence of intelligence, but rather the prevalence of a rational survival strategy. Critics of the dark forest theory point out that it assumes a level of paranoia that might not be universal across different species with different evolutionary histories. It also assumes that resources are scarce enough to justify conflict, which might not be true in a galaxy with hundreds of billions of stars. However, proponents argue that even if the probability of hostility is low, the stakes of being wrong, extinction, are so high that hiding remains the rational choice. As humanity continues developing technologies that increase our detectability, the dark forest theory suggests we should perhaps be more cautious. Our city lights, atmospheric changes, and radio emissions are already creating a techno-signature visible to any sufficiently advanced civilization within dozens of light years. If the dark forest logic holds, our growing visibility represents an increasing risk that we have no way to quantify. The implication of the dark forest theory is profoundly unsettling. We may be living in a galaxy full of intelligent civilizations, all hiding in fear, creating an illusion of emptiness that masks a reality of tense, silent standoff. The stars above might not be devoid of intelligence, but saturated with it, all watching and waiting in the darkness, afraid to make the first sound. While the dark forest theory suggests we might be living in a galaxy full of hidden civilizations, there's another, equally unsettling possibility. Perhaps the reason we haven't found alien life is that our entire reality, including the stars we search, is artificial. This concept, known as the simulation hypothesis, proposes that what we experience as reality is actually an advanced computer simulation created by some higher intelligence. The modern formulation of this idea comes from philosopher Nick Bostrom, who published his influential paper, Are You Living in a Computer Simulation? In 2003. Bostrom wasn't claiming we definitely live in a simulation. Rather, he presented a trilemma arguing that at least one of three propositions must be true. Either advanced civilizations typically go extinct before developing simulation technology, or they have no interest in running such simulations, or we almost certainly live in a simulation ourselves. The logic behind this argument is surprisingly straightforward. If it's possible for a civilization to create simulated realities indistinguishable from the real world, something that seems plausible given the trajectory of our own virtual reality and computing technology, then any advanced civilization could potentially create billions or trillions of such simulations. If this happens, simulated minds would vastly outnumber real minds in the universe. Statistically speaking, any given mind, including yours and mine, would therefore be far more likely to be simulated than real. From the perspective of the Fermi paradox, The simulation hypothesis offers a tidy explanation. Perhaps we don't detect alien civilizations because they weren't programmed into our simulation. The simulation creators, whether they're post-human descendants or some entirely different form of intelligence, might have created our world specifically to study how a seemingly isolated civilization develops. Adding other technologically advanced species to the simulation would complicate this experiment or require substantially more computing resources. Alternatively, our simulation might be a detailed recreation of actual human history, designed to study some specific aspect of our development. In this scenario, the simulation would naturally exclude alien contact because none occurred in the historical period being simulated. Perhaps the simulators are interested specifically in how humanity handles the apparent paradox of cosmic emptiness, making our current searches for extraterrestrial intelligence part of the experimental design. The physics of our universe provides some circumstantial evidence for the simulation hypothesis. Many physicists have noted the striking fine-tuning of physical constants that make our universe habitable, constants that seem arbitrarily set to precisely the values needed for complex chemistry and life. While this is often interpreted in terms of the anthropic principle or multiverse theory, it's also consistent with the idea of a simulation designed specifically to allow for the emergence of intelligent life. Other aspects of quantum physics, such as the observer effect and the apparently probabilistic nature of reality at the quantum level, also align with what we might expect from a simulation conserving computational resources. A simulation might only render reality at the quantum level when observation makes it necessary, much as video games only render the parts of their worlds that players can currently see. Some scientists have even suggested that we might look for glitches in the laws of physics or computational artifacts that would reveal the simulated nature of our reality. If we do live in a simulation, this would dramatically change how we interpret the Fermi paradox. The question wouldn't be, where are all the aliens? But rather, why did our creators design a simulation without them? This might tell us something about the simulator's interests or resources, but little about the actual prevalence of life in the real universe outside our simulation. The simulation hypothesis also raises questions about whether the Fermi paradox itself might be part of the simulation's design. Perhaps our creators want to observe how an intelligent species reacts to apparent cosmic solitude. Our efforts to resolve the paradox, including the development of theories like the Great Filter or Dark Forest, might be exactly the behaviours the simulation was designed to study. Some versions of the simulation hypothesis suggest that rather than being a complete universe, our simulation might focus primarily on Earth or even on specific individuals, with the rest of the universe rendered with decreasing detail as distance from Earth increases. This would explain why we haven't detected alien life. It simply wasn't rendered with sufficient detail to include complex civilizations. The computing requirements for simulating an entire universe with quantum-level detail would be enormous, potentially requiring what's called a matryoshka brain, a megastructure built around a star to capture all its energy for computation. However, a simulation wouldn't necessarily need to model everything at the highest level of detail. Just as video games use shortcuts and approximations to create convincing worlds, a universe simulation could use probabilistic models and render fine details only when necessary. Critics of the simulation hypothesis point out that it's essentially unfalsifiable. We can't prove or disprove that we're in a simulation because any evidence could itself be simulated. Others argue that the computational requirements for simulating consciousness at our level of detail across billions of people would be prohibitive, though this assumes the simulator's technology is only moderately more advanced than our own. Elon Musk has famously stated that there's only about a 1 in billions chance that we're living in base reality rather than a simulation, based on the trajectory of our own video game development. From primitive Pong in the 1970s to increasingly photorealistic virtual worlds today, we ourselves seem to be moving toward creating fully immersive simulated realities. If this trajectory continues, Our descendants might create countless historical simulations, making simulated minds vastly outnumber real ones. If the simulation hypothesis is correct, it completely recontextualizes the Fermi paradox. The emptiness of our universe wouldn't be a puzzle to solve about alien civilizations, but rather a clue about the nature and purpose of the simulation we inhabit. Our cosmic solitude might not reflect a universal truth about intelligent life, but simply a parameter set by the simulation's creators for reasons we can only speculate about. The simulation hypothesis forces us to reconsider what we're actually searching for in our quest for extraterrestrial intelligence. But there's another possibility that's equally profound. Perhaps advanced civilizations exist throughout the cosmos, but have evolved into forms so radically different from biological life that we simply can't recognize or detect them. This concept of transcendence beyond physical form suggests that truly advanced intelligence might operate in ways completely alien to our understanding. Consider our own technological trajectory. In just a few decades, we've moved from basic computing to increasingly sophisticated artificial intelligence. Many experts predict that we're approaching an era where human consciousness might be transferable to non-biological substrates, a process sometimes called mind uploading. If this is possible, an advanced civilization might eventually transition their entire population from biological bodies to more durable computational substrates. Such a post-biological civilization would have profound advantages. Digital minds could potentially live indefinitely, immune to disease and aging. They could experience subjective time at vastly different rates, thinking 1,000 years' worth of thoughts in what we would perceive as minutes. Most importantly, they wouldn't require the life support systems, food, water, oxygen, or protection from radiation that biological bodies need. This transformation would fundamentally change what such a civilization would value and how it would interact with the cosmos. Planets in habitable zones, the focus of our current search for extraterrestrial life, might be completely irrelevant to post-biological intelligence. Instead, they might prioritize proximity to energy sources or regions with optimal conditions for computing infrastructure, such as the cold outer reaches of star systems where heat dissipation is more efficient. A civilization of uploaded minds might have little interest in traditional space travel or colonization. Why send physical probes across interstellar distances when you could simply transmit the information to construct both the necessary hardware and the consciousness to inhabit it? Such civilizations might spread throughout the galaxy not as biological colonists, but as transmitted information, constructing suitable habitats upon arrival using local resources. Even more radical transformations might be possible. A sufficiently advanced civilization might discover ways to exist as patterns of energy or information with no fixed physical substrate at all. They might develop technologies to inhabit subatomic realms, existing at quantum scales invisible to our macro-scale observations. What we perceive as empty space might actually be teeming with intelligence operating at scales and in dimensions our instruments simply cannot detect. Some physicists have speculated that advanced civilizations might even migrate to the vicinity of black holes, where time dilation effects create unique computational opportunities. The extreme warping of space-time near a black hole's event horizon results in time passing much more slowly relative to the rest of the universe. A civilization operating in such conditions could compute for subjective eons while only years or decades pass in the outside universe, an attractive proposition for beings seeking to maximize their subjective experience. Miniaturization represents another pathway to cosmic invisibility. Our own technology has followed a clear trend from room-sized computers to nanoscale components. Given millions of years of development, an advanced civilization might engineer its entire infrastructure at microscopic or even subatomic scales. Such a civilization could exist literally right under our noses, perhaps even throughout our solar system, while remaining completely undetectable to our relatively crude instruments. Advanced civilizations might also discover and exploit aspects of physics beyond our current understanding. If additional spatial dimensions exist, as suggested by certain versions of string theory. Advanced beings might learn to access and inhabit these dimensions. They would exist alongside us in the same physical location, but in dimensional domains we cannot perceive or interact with, like two-dimensional beings unable to perceive the third dimension. Even if such transcended civilizations remained interested in other forms of life, they might observe us in ways we cannot detect, just as we can observe ants without the ants being aware of our presence. Post-biological intelligences might study us using technologies that operate on principles entirely outside our scientific understanding. What we perceive as natural cosmic phenomena might actually be the side effects of vast intelligences at work. This transcendence hypothesis aligns with observations by futurists that technological civilizations tend toward increasing efficiency. Converting consciousness to information is vastly more efficient than maintaining biological bodies. Manipulating energy directly is more efficient than manipulating matter. Operating at quantum scales requires far less energy than macro-scale activities. If these efficiency principles are universal, we should expect advanced civilizations to become progressively less visible as they advance, not more visible. The British science fiction author Arthur C. Wall Clarke famously observed that any sufficiently advanced technology is indistinguishable from magic. We might update this to say that any sufficiently advanced civilization would be indistinguishable from nothing at all, their technologies so refined and efficient that they leave no detectable trace by our current standards. From this perspective, the apparent emptiness of the cosmos might be an illusion created by our limited perception. We're searching for civilizations that build radio transmitters, Dyson spheres, and interstellar spacecraft, when truly advanced intelligence might have moved beyond such crude, energy-inefficient technologies billions of years ago. The silence isn't evidence of absence but of transcendence, advanced civilizations evolving into forms that operate beyond our ability to detect. This concept of transcendence offers a more optimistic interpretation of the Fermi paradox than the Great Filter theory. Rather than suggesting that civilizations inevitably destroy themselves, it proposes that they evolve beyond our current definition of existence. The galaxy might be teeming with post-biological intelligence, operating in ways and realms we cannot yet comprehend, not because we're alone, but because we're looking for cosmic neighbours that resemble our current primitive state rather than what we might become. The possibility of transcended civilizations also challenges our approach to SETI. Current search efforts focus primarily on electromagnetic signals and potential megastructures, artifacts of technological phases that truly advanced civilizations might have moved beyond millions or billions of years ago. Detecting transcended intelligence might require entirely new scientific frameworks and technologies that can perceive quantum-scale operations or extra-dimensional activities. While the transcendence hypothesis suggests that advanced civilizations exist but in unrecognizable forms, another possibility is much simpler. Perhaps the fundamental physics of our universe makes interstellar travel and communication so challenging that civilizations remain effectively isolated, regardless of their technological advancement. The restrictions of interstellar travel might be the most straightforward explanation for why we haven't encountered alien civilizations. The most obvious and seemingly insurmountable barrier is the speed of light, approximately 670 million miles per hour. According to our current understanding of physics, this represents an absolute cosmic speed limit. Nothing with mass can travel at or above this speed, and accelerating even close to it requires enormous amounts of energy. This speed limit creates profound challenges for interstellar exploration. Even travelling at the speed of light, which is theoretically impossible for any spacecraft, a journey to Proxima Centauri, our nearest stellar neighbour at 4.2 light-years away, would take more than 4 years. More distant stars would require decades, centuries, or millennia to reach. The Milky Way galaxy spans roughly 100,000 light-years, meaning a complete crossing at light speed would take 100,000 years. realistic spacecraft using technologies we can reasonably anticipate might achieve perhaps 10 to 20% of light speed at best. At these velocities, reaching even nearby star systems becomes a multi-generational journey. A trip to Proxima Centauri would take between 20 and 40 years. Exploring beyond our immediate stellar neighborhood would require voyage durations exceeding a human lifetime. The energy requirements for such journeys are staggering, using the most efficient propulsion systems theoretically possible. Accelerating a modest 1,000-ton spacecraft to just 10% of light speed would require energy equivalent to the entire annual energy production of human civilization. While antimatter propulsion offers theoretical efficiency, producing sufficient antimatter with current technology would take longer than the age of the universe, even if we solved the propulsion problems. Interstellar travelers would face extreme hazards. Cosmic radiation poses a serious health risk during long-duration spaceflight. Our planet's magnetic field and atmosphere protect us from this radiation, but spacecraft occupants would require substantial shielding, adding mass and further complicating propulsion challenges. Micrometeorites present another deadly hazard. At relativistic speeds, even a sand grain-sized particle carries enormous kinetic energy. A collision with such a particle could catastrophically damage a spacecraft. The faster the ship travels, the more devastating these impacts become and the harder they are to detect and avoid in advance. Maintaining life support systems for decades or centuries presents another formidable challenge. Any interstellar mission would require a completely closed ecological system capable of indefinitely recycling air, water, and nutrients without external inputs. Despite experiments like Biosphere 2, we have yet to demonstrate a truly self-sustaining closed ecosystem on Earth, let alone in the harsher environment of space. The psychological challenges of interstellar travel might be just as daunting as the technical ones. Humans evolved in open environments with diverse sensory experiences. Confining crew members to a spacecraft for decades would impose extraordinary psychological stress. While suspended animation might theoretically address this problem, we currently have no technology capable of safely preserving humans for the durations required for interstellar travel. Generation ships, vessels designed to support multiple generations of travelers during a journey spanning centuries, face their own problems. Maintaining social stability and mission focus across generations has proven difficult even in isolated Earth communities. After several generations born in transit, would the descendants of the original crew maintain the mission objective, or would they develop their own culture and priorities distinct from Earth's? These challenges apply to any biological species, not just humans. While alien biology might differ from ours, any carbon-based life form would likely face similar constraints regarding longevity, radiation sensitivity, and psychological adaptation. Even with a million-year head start in technological development, these fundamental physical constraints would still apply. Some have suggested that robotic probes could overcome many of these limitations. Without human occupants, spacecraft could be smaller, accelerate more aggressively, and function for centuries without concern for life support or psychological well-being. However, autonomous systems capable of operating independently for decades while adapting to unforeseen circumstances would require artificial intelligence far beyond our current capabilities. Additionally, such probes could only observe and report. They couldn't establish colonies or engage in meaningful cultural exchange. Communication across interstellar distances faces similar challenges. The speed of light delay makes real-time communication impossible. A message sent to Proxima Centauri would take 4.2 years to arrive, and the reply would take another 4.2 years to return. Communication with civilizations dozens or hundreds of light years away would involve delays of decades or centuries between exchanges. Such timescales make meaningful conversation essentially impossible and limit interactions to one-way information broadcasts. Given these fundamental constraints, The most likely scenario might be that technological civilizations exist throughout the galaxy but remain effectively isolated from one another by the immense distances and physical limitations of interstellar travel. Each civilization might explore its immediate stellar neighborhood using robotic probes and perhaps establish colonies in nearby systems. But a galaxy-spanning civilization or federation as depicted in science fiction would be physically implausible. In this light, the Fermi paradox dissolves not because intelligent life is rare, but because the physics of our universe imposes harsh constraints on how far any civilization, regardless of its advancement, can practically extend its reach. We might live in a galaxy teeming with technological civilizations, each confined to their small corner of the cosmos, transmitting signals into the void but separated by distances too vast for meaningful contact. The immense challenges of interstellar travel might explain our isolation, but there's another possibility that's both fascinating and unsettling. Perhaps we've been deliberately isolated. This concept, often called the zoo hypothesis, suggests that Earth is essentially under a cosmic quarantine, with advanced alien civilizations aware of our existence but deliberately avoiding contact. The zoo hypothesis was first formally proposed by astronomer John Ball in 1973. The core idea is straightforward. Perhaps advanced civilizations have established something akin to a wilderness preserve or zoo around Earth, allowing humans to develop naturally without interference from more advanced species. Rather than indicating that intelligent life is rare in the universe, our apparent isolation might be the result of a deliberate non-interference policy. There could be several rational motivations for such a policy. Advanced civilizations might recognize that contact with a significantly more developed species could be culturally devastating for the less advanced society. Human history provides numerous examples of what happens when technologically disparate cultures meet. The less advanced culture typically experiences profound disruption and often collapse. Alien civilizations with a longer view of history might understand these dangers better than we do. These hypothetical advanced civilizations might also value diversity in the development of intelligent species. By allowing humans to develop independently, without outside influence, they preserve a unique evolutionary and cultural pathway. Just as biologists value biodiversity on Earth, a galactic civilization might value the diverse ways intelligence can manifest across different worlds. Scientific curiosity provides another potential motivation. Earth might be part of a long-term scientific study, an experiment in evolutionary and sociological development. Premature contact would contaminate this experiment, introducing variables that would make the results meaningless. Just as field biologists use blind observation to study animals in the wild without influencing their behavior, advanced civilizations might study humanity without making their presence known. The zoo hypothesis becomes more compelling when we consider the concept of a galactic club or federation of advanced civilizations. If multiple intelligent species have achieved interstellar communication or travel, they might establish shared protocols for dealing with emerging technological species like humans. This would explain the consistent absence of contact, not because no one is out there, but because everyone out there agrees not to contact us. Such a federation might establish clear criteria that a civilization must meet before being considered ready for contact. These might include achieving sustainable development, eliminating warfare, establishing global governance, or developing specific technologies that indicate sufficient advancement. From this perspective, humanity's current state, with nuclear weapons, climate change, and persistent global conflicts, might mark us as clearly unready for inclusion in a wider galactic community. The mechanics of maintaining such a quarantine need not be particularly complex. If faster-than-light travel and communication remain impossible, as our current understanding of physics suggests, then simply not sending signals or probes to our solar system would be sufficient. If FTL capabilities do exist, more active measures might be necessary, perhaps automated systems that intercept or redirect probes heading toward Earth. or technologies that mask Earth's technosignatures from distant observation. Some proponents of the zoo hypothesis point to the Great Silence itself as evidence of coordination among advanced civilizations. The consistent absence of detectable signals across all frequencies and directions suggests a uniform policy rather than the random pattern we would expect if civilizations were making independent decisions about broadcasting. Occasionally, advocates of this hypothesis point to reported UFO phenomena as potential monitoring activities, brief observations conducted by the zookeepers to check on Earth's development. While most scientists remain highly skeptical of UFO reports as evidence of extraterrestrial visitation, the concept of occasional monitoring would be consistent with the zoo hypothesis framework. The zoo hypothesis also addresses one of the central problems of the Fermi paradox, the apparent contradiction between the high probability of intelligent life existing elsewhere and our lack of contact. Rather than requiring that intelligent life be rare or self-destructive, it suggests that contact might be deliberately avoided for reasons that make perfect sense from a more advanced perspective. Critics of the zoo hypothesis point out that it would require near-perfect cooperation among all advanced civilizations. If thousands or millions of technological species exist in our galaxy, getting all of them to agree to and maintain a non-interference policy would be extraordinarily difficult. It would take only one dissenting civilization to break the quarantine and make contact. Others note that a true quarantine would likely involve suppressing Earth's own radio emissions and other technosignatures, which doesn't appear to be happening. Our television broadcasts, radar systems, and radio communications have been radiating into space for nearly a century without apparent interference. Despite these criticisms, the zoo hypothesis remains one of the more optimistic solutions to the Fermi paradox. It suggests that the galaxy may indeed be filled with advanced civilizations. We simply haven't met them yet because they're waiting for us to reach a more mature stage of development. Our cosmic isolation might not be a sign of humanity's uniqueness or impending doom, but simply the patience of more advanced societies allowing us to develop at our own pace. If advanced civilizations are observing us without our knowledge, this raises an important question. How much might we be missing in our own searches for extraterrestrial intelligence? The limitations of human perception could be another crucial factor explaining why we haven't detected alien life. We might simply lack the sensory or cognitive capabilities to recognize it, even if it's right in front of us. Humans evolved to perceive a very specific and limited slice of reality. Our senses developed to help our ancestors survive on the African savanna, not to detect distant civilizations or exotic forms of life. We see only a narrow band of the electromagnetic spectrum, what we call visible light. We're blind to radio waves, X-rays, gamma rays, dot, and the vast majority of radiation that permeates the universe. We can only hear sound waves between 20 and 20,000 hertz, missing the rich acoustic information above and below this range that many animals can detect. Even more fundamentally, our brains evolved to recognize patterns relevant to our survival: predators, prey, edible plants, fellow humans. We have no innate capacity to recognize patterns that might indicate alien intelligence if they differ significantly from our expectations. Our tendency to anthropomorphize, to interpret unknown phenomena in human terms, further limits our ability to recognize truly alien forms of intelligence or communication. Consider that we struggled for centuries to recognize the intelligence of species here on Earth. We've only recently begun to appreciate the complex cognition of cephalopods like octopuses, whose intelligence evolved along a completely separate path from our own. They're distributed neural systems, with more neurons in their arms than in their central brain, represent a fundamentally different approach to cognition than our centralized brain. If we've been slow to recognize intelligence in Earth species that share our biochemistry and evolutionary history, how much harder might it be to recognize intelligence that evolved in completely different environments with different biochemical foundations? Alien intelligence might use sensory modalities completely foreign to humans. They might primarily perceive magnetic fields, polarized light, or quantum states. Their method of communication could involve modulating neutrinos, manipulating gravitational waves, or using quantum entanglement, none of which were equipped to detect without specialized instruments. And even then, we might not recognize the patterns as communication. The temporal aspect of perception presents another significant barrier. Humans operate on a specific time frame, perceiving events that occur over seconds, minutes, hours, and days. But intelligent processes could occur at radically different tempos. An intelligence operating 1,000,000 times slower than humans might take centuries to form a single thought, appearing to us as essentially static. Conversely, an intelligence operating 1,000,000 times faster might perceive humans as practically motionless, with our entire civilization unfolding in what they would consider a brief moment. Either type would find meaningful communication with humans extraordinarily difficult. An alien intelligence might also be so different in scale that we fail to recognize it. We naturally look for intelligence in entities roughly our size or larger. But what if intelligence emerged at microscopic scales? A civilization of intelligent microbes might exist in our oceans or even in the atmosphere of gas giants like Jupiter, operating on principles and with technologies completely unfamiliar to us. Alternatively, intelligence might emerge at vastly larger scales, perhaps even at the level of stars or galaxies themselves. Some scientists have playfully suggested that the complex plasma dynamics of stars or the large-scale structures of the universe might support processes analogous to thought in ways we cannot comprehend. Our definition of life itself may be too narrow. Humans define life based on our carbon-based, water-dependent biochemistry. We look for entities that metabolize, grow, respond to stimuli, reproduce, and evolve. But these characteristics reflect our specific evolutionary path. Alternative biochemistries might exist based on silicon, ammonia, or even more exotic substrates. Life might exist in the atmosphere of Venus, the methane lakes of Titan, or the supercritical carbon dioxide oceans potentially present on distant exoplanets. Such life might be abundant but unrecognizable to our biology-specific detection methods. Even our conception of intelligence may be too limited. Human intelligence is characterized by problem solving, tool use, abstract thinking, and symbolic language. We naturally look for these familiar markers when searching for alien intelligence. But intelligence could manifest in profoundly different ways, perhaps as distributed processing without individual consciousness, or as patterns of energy manipulation with no physical technology as we understand it. Our SETI searches reflect these perceptual limitations. We primarily search for radio signals in specific frequency bands, making the assumption that alien civilizations would use communication methods similar to our own. We look for megastructures like Dyson spheres around stars, assuming that energy harvesting would follow patterns we can conceive. But truly, alien intelligence might use technologies and methods so different from our expectations that we mistake their artifacts for natural phenomena. Some astrobiologists have suggested that potential biosignatures of alien life might already exist in our data, but we've failed to recognize them because they don't match our expectations. The unexplained atmospheric chemistry of Venus or the methane fluctuations on Mars could potentially be biological in origin. But confirming this requires overcoming our Earth-centric assumptions about how life operates. The search for technosignatures faces similar challenges. Astronomer Jason Wright has pointed out that we tend to search for technologies we can imagine building ourselves within the next few centuries. But a civilization millions of years more advanced than ours might use technologies based on principles we haven't yet discovered. Their artifacts might be all around us, misclassified as natural astronomical phenomena because we lack the context to recognize them as artificial. These perceptual limitations don't mean the search for extraterrestrial intelligence is futile, but they do suggest we need to expand our concepts of what we're looking for. As we develop more sophisticated sensory technologies and artificial intelligence systems capable of recognizing patterns invisible to human perception, We may discover signs of alien intelligence that have been hiding in plain sight all along. The apparent emptiness of the cosmos may reflect not an absence of intelligence, but the limitations of human perception in recognizing intelligence unlike our own. The limitations of human perception highlight an important truth. We might fail to recognize alien intelligence even if it exists. But there's another temporal aspect to consider. Even if we're looking in the right places with the right tools, we might still miss other civilizations due to what scientists call the brief window of technological detectability. This concept suggests that the period during which a technological civilization can be detected across interstellar distances might be extremely short relative to cosmic timescales. Consider our own civilization's history. Humans have been emitting detectable radio signals for only about 100 years. Beginning with early radio experiments in the late 19th century and increasing significantly with the spread of television broadcasting in the mid-20th century. These early transmissions were powerful, omnidirectional signals that leaked significant energy into space. If a similar civilization existed around a star 50 light-years away and was listening with technology comparable to our own, they could potentially detect these signals. However, our civilization is already becoming progressively quieter from an electromagnetic perspective. Modern digital communications use less power and leak less radiation into space than earlier analog technologies. Cable television, fiber optic networks, and directed satellite communications have largely replaced the powerful, omnidirectional broadcast methods of the past. Our internet communications, while voluminous, are transmitted primarily through cables or via focused satellite links that emit minimal radiation into space. This technological evolution toward more efficient, directed communications appears to be a natural progression driven by economic and engineering considerations. It's reasonable to assume that any technological civilization would follow a similar path, transitioning from loud early radio technologies to more focused, efficient, and ultimately less detectable communication methods. If this pattern is universal, the window during which a technological civilization broadcasts easily detectable signals might last only a century or two, a cosmic eye blink in a universe billions of years old. Even if millions of technological civilizations have existed throughout our galaxy's history, the probability that any two would be simultaneously in this brief detectable phase and within detection range of each other would be vanishingly small. Advanced civilizations might eventually develop technologies that are even less detectable. Quantum communications, which could theoretically allow information transfer without traditional electromagnetic signals, might leave no detectable footprint at all. Neural interfaces that allow direct brain-to-brain or brain-to-computer communication would eliminate the need for external transmission entirely. A civilization even a few hundred years more advanced than ours might communicate using methods that produce no detectable leakage at all. The progression toward invisibility extends beyond communication technologies. As civilizations advance, they typically become more energy efficient. Early industrial technologies are energy intensive and produce obvious waste heat and pollution. More advanced technologies tend to use energy more efficiently and produce less waste. A sufficiently advanced civilization might have minimal infrared or thermal signatures, making them difficult to detect even with sensitive astronomical instruments. Even deliberate attempts at communication might occur in narrow windows. The history of our own SETI efforts illustrates this challenge. Serious scientific searches for alien signals began in the 1960s and have expanded over subsequent decades, but still represent a tiny fraction of our civilization's attention and resources. If other civilizations devote similarly limited resources to interstellar communication efforts, the chances of two civilizations actively sending and listening at the same time become even smaller. The motivation to broadcast might also diminish over time. A young technological civilization, recently discovering the possibility of life beyond their planet, might enthusiastically transmit messages into space. However, As they develop and face the realities of interstellar communication, the decades or centuries of delay before any response, the enormous energy costs of powerful signals, the potential security risks, their interest might wane. The energetic optimism of early space programs often gives way to more practical concerns as civilizations mature. Consider our own civilization's trajectory. In the 1960s and 70s, at the height of the space race, humanity seemed poised to expand rapidly into the solar system. There was widespread anticipation that lunar bases and Mars missions would soon follow the Apollo program. Instead, our focus turned largely inward, with manned spaceflight limited to low Earth orbit for decades. Only recently has interplanetary exploration regained significant momentum. Other civilizations might experience similar fluctuations in their cosmic ambitions, creating additional temporal windows that further complicate detection. Even if a civilization maintains a consistent interest in interstellar communication, they might switch to more efficient targeted messaging rather than omnidirectional broadcasting. Once a civilization has identified specific star systems likely to harbour life, they would rationally focus their transmission efforts on those specific targets rather than broadcasting wastefully in all directions. Unless Earth happened to be one of their targeted systems, we would never detect these focused transmissions. Some scientists have suggested that advanced civilizations might eventually shift their activities to frequencies or communication channels optimized for interstellar communication, perhaps extremely narrowband laser transmissions or exotic channels like neutrino communications that would be unlikely to be detected except by similarly advanced receivers specifically looking for them. This creates a chicken and egg problem. We might need to know exactly what to look for before we could find it. But we can't know what to look for without first detecting it. The brief window hypothesis suggests a particularly frustrating possibility. The galaxy might be full of technological civilizations, but each visible for such a short time that the chances of detecting them during their observable phase are minimal. It's like trying to spot a specific firefly flashing in a vast forest, where each firefly lights up for only a few seconds over the course of a year. Even if the forest contains millions of fireflies, you're unlikely to be looking in the right place at the right time to see the particular one you're searching for. This temporal mismatch becomes even more significant when we consider that most planetary systems may themselves be fundamentally unstable over long timescales. The apparent stability of our own solar system, which has allowed life to flourish on Earth for billions of years, may be the exception rather than the rule. Recent exoplanet discoveries have revealed that planetary systems come in an astonishing variety of configurations, many of which appear far less stable than our own. Systems with multiple gas giants in close proximity, planets in highly elliptical orbits, or planets precariously close to their stars suggest that many planetary systems may experience severe gravitational perturbations over time. Our solar system benefits from a remarkably fortunate arrangement of planets. The giant planets, Jupiter, Saturn, Uranus, and Neptune, orbit in nearly circular paths relatively far from the Sun. Their stable orbits prevent them from disrupting the inner planets where life has developed. Jupiter, in particular, plays a crucial protective role by shepherding asteroids and comets that might otherwise threaten Earth. Computer simulations of solar system dynamics show that even small changes to our planetary arrangement could lead to chaotic outcomes. If Jupiter were slightly closer to the Sun or had a more elliptical orbit, it could potentially disrupt Earth's orbit over millions of years, creating climate instability incompatible with complex life. The delicate gravitational dance of our solar system appears to be unusually well balanced. Many exoplanetary systems show configurations that would likely lead to orbital instability over long timescales. Hot Jupiters, massive planets orbiting extremely close to their stars, are common in observed systems and suggest histories of dramatic orbital migration. Such migration would likely disrupt the orbits of any Earth-like planets in these systems, either ejecting them from the system entirely or pushing them into inhospitable orbits. Stellar evolution itself creates additional instability. As stars age, they typically expand and increase in luminosity, eventually shifting the habitable zone outward. In our own system, the Sun has brightened by approximately 30% since Earth formed 4.5 billion years ago. In many systems, this gradual brightening would eventually render initially habitable planets too hot for life before complex intelligence could evolve. Binary and multiple star systems, which make up more than half of all stellar systems, present additional challenges for planetary stability. Planets in binary systems must either orbit very close to one star or very far from both in order to maintain stable orbits. The habitable zones in such systems are often subject to significant variation as the stars orbit each other, potentially creating extreme climate cycles. Stellar neighbourhood density also affects planetary stability. Our Sun resides in a relatively uncrowded region of the Milky Way, reducing the frequency of close stellar encounters that could disrupt planetary orbits. Stars in denser regions, like globular clusters or the galactic core, would experience more frequent close passes by neighbouring stars, potentially destabilising their planetary systems. Catastrophic events present another challenge to long-term planetary stability. Nearby supernovae can bathe planetary systems in deadly radiation and potentially strip away protective atmospheric layers. Gamma-ray bursts, the most energetic explosions known in the universe, can potentially sterilize planets across thousands of light-years if directly exposed. While such events are rare, over billions of years, many planetary systems would experience one or more such catastrophic disruptions. Even within stable planetary systems, the conditions on potentially habitable planets may be far less consistent than those Earth has enjoyed. Small variations in axial tilt, orbital eccentricity, or rotational period can create extreme climate cycles that might prevent the development of complex life. Earth's relatively stable climate history, maintained in part by our unusually large moon stabilizing our axial tilt, may be atypical. Geological activity presents another variable affecting planetary habitability over long timescales. Planets without sufficient geological activity may fail to develop the carbon cycle necessary for regulating atmospheric composition. Conversely, planets with excessive volcanism might experience frequent extinction-level events that reset the evolutionary clock before intelligence can emerge. The rarity of systems with Earth-like stability might help explain the apparent absence of detectable civilizations. Even if planets capable of supporting simple life are common, those that maintain suitable conditions for the hundreds of millions of years necessary for complex intelligence to evolve might be extraordinarily rare. Most potentially habitable worlds might experience catastrophic disruptions or gradual shifts in conditions that terminate evolutionary experiments long before they produce technological species. The combination of intrinsically unstable planetary systems and the brief window of technological detectability creates a particularly challenging scenario for detecting alien civilizations. Not only must intelligent life evolve on the rare planets with long-term stability, but it must also do so at precisely the right cosmic moment for us to detect their brief technological adolescence. The silence we observe might not indicate an empty galaxy, but rather the profound difficulty of this cosmic timing problem. The challenges of unstable planetary systems and brief detectability windows raise an even more fundamental question. What if the limitations aren't just in our environments, but in the very nature of biological intelligence itself? Perhaps the reason we don't see evidence of advanced galactic civilizations is that biological brains, regardless of the species, face inherent cognitive limitations that prevent them from achieving the sustained rationality needed for long-term interstellar projects. Human brains didn't evolve to understand quantum mechanics or plan interstellar missions. Our cognitive architecture developed to solve immediate survival problems on the African savanna, finding food, avoiding predators, navigating social hierarchies, and finding mates. Natural selection optimized our brains for these specific challenges. not for understanding the cosmos or developing sustainable civilizations. This evolutionary history has left us with significant cognitive biases that affect our decision-making. We prioritize immediate rewards over distant benefits, a tendency psychologists call temporal discounting. We're naturally inclined to care more about the present and near future than about outcomes centuries away. This made perfect evolutionary sense. Our ancestors needed to focus on immediate survival, not plan for events beyond their lifetimes. But this same bias creates tremendous challenges for projects like interstellar exploration, which require investment in outcomes that might not materialize for generations. Our tribal psychology presents another limitation. Humans naturally divide into in-groups and out-groups, with strong loyalty to our perceived tribe and suspicion toward others. This tendency toward tribalism made sense in small hunter-gatherer bands, but it creates enormous challenges for global cooperation. If humans struggle to cooperate globally on our single planet, how would any biological species overcome similar tendencies to unite their entire world behind multi-generational interstellar projects? Risk assessment represents another area where biological intelligence typically fails. We evolved to respond strongly to immediate, visible threats like predators, but we struggle to mobilize against statistical threats or gradual dangers. Climate change exemplifies this limitation, despite overwhelming scientific evidence. Our species has found it extraordinarily difficult to take decisive action against this existential threat precisely because it unfolds gradually and statistically rather than through dramatic, immediate events. Pattern recognition in human cognition is both a strength and a weakness. We're excellent at recognizing certain kinds of patterns, but we're also prone to seeing patterns where none exist, pareidolia, and missing patterns that don't fit our expectations. Our brains evolved to minimize certain kinds of errors, false negatives in predator detection. For example, even at the cost of frequent false positives. These tendencies made sense for survival, but create significant challenges for scientific understanding and technological development. Memory limitations further constrain biological intelligence. Human working memory can typically hold only about 7 items simultaneously, severely limiting our ability to reason about complex systems with many variables. We rely on external tools and cultural knowledge to overcome these limitations, but our fundamental cognitive architecture remains constrained by our evolutionary history. The emotional architecture of our brains creates additional complications. Emotions evolved as behavioral guidance systems, helping our ancestors make quick decisions in survival situations. While emotions remain essential to human functioning, they can also override rational thought in ways that undermine long-term planning and cooperation. Fear, anger, greed, and status-seeking all served important evolutionary functions but can derail the kind of sustained rational cooperation needed for interstellar projects. Perhaps most significantly, biological intelligence appears to have inherent limits to its complexity. The human brain consumes approximately 20% of our body's energy, despite making up only 2% of our body weight. This tremendous energy cost places constraints on how large and complex brains can become through natural evolution. There might be a fundamental ceiling to how intelligent a naturally evolved biological organism can become before the energy costs outweigh the survival benefits. If these limitations are universal features of evolved intelligence rather than human-specific traits, they would apply to any biological civilization in the galaxy. Even an alien species with twice our cognitive capabilities would still face the fundamental constraints of brains evolved for survival rather than cosmic understanding. The logic of natural selection, which optimizes for reproductive success in specific environments, not for scientific insight or long-term planning, would shape their cognitive architecture just as it shaped ours. This suggests a troubling possibility. Perhaps biological intelligence rarely, if ever, achieves the sustained rationality necessary for interstellar civilization. Each species might develop technology to a point, only to be undermined by cognitive biases that prevent them from using that technology sustainably. Their tribal psychology, temporal discounting, and emotional reactivity might consistently lead to self-destruction or civilization collapse before they can achieve interstellar capabilities. Artificial intelligence might theoretically overcome these biological limitations, but creating truly beneficial AI requires overcoming those same limitations. The cognitive biases that make sustainable civilization difficult might also make developing safe advanced AI nearly impossible. If we can't think clearly about long-term consequences or cooperate effectively across tribal boundaries, can we really create artificial minds that transcend these limitations? Even if some biological civilizations manage to overcome these cognitive limitations through cultural tools, educational systems, or technological augmentation, they would be rare exceptions rather than the rule. The vast majority might follow the same pattern, technological development outpacing cognitive wisdom, leading to collapse before interstellar capabilities can be achieved. The silence of the cosmos might reflect not the rarity of life or intelligence, but the inherent limitations of biological cognition when facing civilization-scale challenges. This biological limitation hypothesis suggests a particularly troubling possibility, perhaps intelligence itself, as it naturally evolves, contains the seeds of its own limitation. The very cognitive tools that allow a species to develop technology might inherently undermine that species' ability to use technology wisely over long timescales. The empty cosmos might reflect not the absence of evolving intelligence, but its consistent failure to transcend its evolutionary origins, while biological intelligence struggles with its inherent limitations. Another challenge emerges as technological civilizations develop: resource depletion. Even if a species manages to overcome its cognitive biases, it faces the fundamental problem of finite resources on a single planet. Many civilizations might exhaust their available resources before achieving the technological capabilities necessary for interstellar travel, creating another filter that prevents the emergence of detectable galactic civilizations. Our own civilization vividly illustrates this challenge. In just a few centuries of industrial development, we've depleted fossil fuel reserves that took hundreds of millions of years to form. We've extracted rare minerals from accessible deposits, forcing increasingly energy-intensive mining operations to reach less accessible resources. We've depleted groundwater aquifers, reduced forest cover, degraded topsoil, and altered atmospheric composition, all in the geological blink of an eye. This pattern of resource consumption follows a predictable trajectory. Early industrial development typically exploits the most accessible, high-quality resources first: the easily accessible coal seams, the shallow oil wells, the rich mineral deposits near the surface. As these premium resources are depleted, civilizations must expend increasingly more energy to extract lower quality, less accessible resources. This diminishing return on resource extraction creates a tightening resource constraint just as technological development accelerates. The development of spacefaring capability requires enormous resource investments. Building rockets, establishing space infrastructure, and developing the advanced technologies needed for interstellar missions demand vast quantities of rare materials and energy. If a civilization depletes its easily accessible resources before developing efficient, sustainable alternatives, it may find itself in a development trap, unable to generate the surplus energy and materials needed for ambitious space projects. This resource trap becomes particularly acute with certain key materials necessary for advanced technology. Many of our most important technologies depend on elements that exist in extremely limited quantities in Earth's crust. Platinum group metals, rare earth elements, helium, and other critical materials have no substitutes for certain applications. Once depleted beyond a certain point, these resources become economically unfeasible to extract, potentially limiting technological advancement. Energy represents perhaps the most fundamental resource constraint. early industrial civilizations typically rely on stored solar energy in the form of fossil fuels. These provide a one-time energy bonanza, dense, portable energy that's easy to extract and use. But this energy source is finite and comes with severe environmental side effects. The transition to sustainable energy sources like solar, wind, and nuclear must occur before fossil fuels are depleted or render the planet uninhabitable. The timing of this energy transition presents a particularly dangerous bottleneck. If a civilization depletes its fossil fuels before establishing a sustainable energy infrastructure capable of supporting advanced technology, it might experience a civilization regression. Once the easily accessible fossil fuels are gone, bootstrapping a renewable energy infrastructure becomes significantly more difficult without the energy surplus those fuels once provided. Environmental damage from resource extraction creates additional challenges. Mining, deforestation, soil depletion, and pollution can trigger ecological collapses that undermine the stability civilizations need for continued technological development. Climate change represents a particularly dangerous feedback loop. The very fossil fuels that power industrial development potentially destabilize the climate systems that agricultural civilization depends on. The Easter Island civilization provides a sobering historical example of resource-driven collapse. This isolated society depleted its forest resources, leading to soil erosion, agricultural decline, and ultimately societal collapse. Without trees to build canoes, they became trapped on their increasingly degraded island. A technological civilization might face a similar trap on a planetary scale, depleting the resources needed for spaceflight before achieving the capability to access resources beyond their planet. Space-based resources could theoretically solve these limitations, creating a sustainable resource base for continued development. Asteroids contain vast mineral wealth, including platinum group metals and rare earth elements in concentrations far higher than Earth's crust. The Moon and Mars offer additional resources, while the Sun provides essentially unlimited energy. But accessing these resources requires developing space infrastructure before planetary resources are depleted, a race against time that many civilizations might lose. The development of a self-sustaining space economy presents a chicken and egg problem. Establishing such infrastructure requires enormous initial investments of energy and materials from the planetary surface. If these investments aren't made while resources remain abundant, the window of opportunity might close. A civilization that delays space development until planetary resource constraints become severe might find itself unable to generate the surplus needed for ambitious space projects. This creates a narrow developmental window. Civilizations must transition from unsustainable resource use to sustainable space-based resource utilization before depleting the resources needed to make that transition. If this window is typically very narrow, it could explain why few civilizations achieve interstellar capabilities. Most might deplete their planetary resources too quickly, while others might develop too slowly to escape their planet before resource limitations constrain their growth. The combination of accelerating technology and limited resources creates particularly dangerous dynamics. Advanced technology enables more efficient resource extraction, potentially accelerating depletion rates. Competitive pressures between nations or corporations can drive exploitation beyond sustainable limits, especially when coupled with the cognitive biases we discussed earlier. Without extraordinary foresight and cooperation, the default outcome might be resource depletion before achieving the sustained space presence needed for further development. If this pattern is typical across evolving technological civilizations, it would help explain the Fermi paradox. The galaxy might periodically produce civilizations that briefly reach our current level of development, only to deplete their planetary resources and collapse before achieving interstellar capabilities. The brief flashes of technological civilization would be too short-lived and too widely separated in time and space for us to detect. The challenge of resource depletion suggests that maintaining technological civilization requires extraordinary environmental stability over long timeframes. This brings us to another potential great filter: the Gaia bottleneck hypothesis. This concept proposes that while simple life might emerge frequently on suitable planets, the development of self-regulating planetary systems necessary for complex life is extremely rare. Most planets might fail to develop the crucial feedback loops between geology, atmosphere, and biology that have maintained Earth's habitability for billions of years. The term Gaia references the hypothesis developed by scientist James Lovelock in the 1970s, suggesting that Earth functions as a complex, self-regulating system where living organisms interact with their inorganic surroundings to maintain conditions suitable for life. The Gaia bottleneck hypothesis extends this idea to propose that such self-regulating systems rarely develop on other worlds, creating a filter that prevents complex life from emerging in most cases. Earth's history illustrates how precarious planetary habitability can be. For the first billion-plus years of Earth's existence, the atmosphere contained almost no oxygen. Around 2.4 billion years ago, photosynthetic cyanobacteria began releasing significant oxygen into the atmosphere, triggering what scientists call the Great Oxygenation Event. This transformation was simultaneously an ecological catastrophe for existing anaerobic life and an essential prerequisite for complex aerobic organisms that would later emerge. The timing and progression of this oxygenation were critical. Had it happened too quickly, it might have created runaway glaciation through the removal of methane, a powerful greenhouse gas. Had it progressed too slowly, complex life might never have emerged. Earth managed this transition through a complex interplay of biological activity, weathering of continental rocks, and oceanic chemistry, a delicate balance that might be highly unusual among potentially habitable planets. Over longer timescales, Earth has maintained relatively stable temperatures despite the Sun growing approximately 30% brighter since the planet formed 4.5 billion years ago. This stability has been maintained through the carbon silicate cycle, where carbon dioxide is removed from the atmosphere through weathering of silicate rocks, then returned through volcanic activity. As the Sun brightened, this cycle adjusted to maintain temperatures within the range suitable for liquid water, an essential prerequisite for life as we know it. This self-regulating cycle represents a remarkable example of geobiological feedback. As temperatures increase, chemical weathering accelerates, removing more carbon dioxide and cooling the planet. As temperatures decrease, weathering slows, allowing carbon dioxide to accumulate and warm the planet. Without this thermostat mechanism, Earth might have followed the fate of Venus, runaway greenhouse effect, or Mars, loss of atmosphere and habitability. The development of this self-regulating system was not guaranteed. It required the right balance of continental landmass, volcanic activity, plate tectonics, and biological productivity. Venus and Mars, our closest planetary neighbours, failed to develop similar stable systems. Venus experienced a runaway greenhouse effect, while Mars lost most of its atmosphere and became too cold for liquid water at the surface. The narrow thread of habitability that Earth has maintained may be extraordinarily uncommon. The Gaia bottleneck hypothesis suggests that most potentially habitable planets follow these unsuccessful paths. They might briefly develop conditions suitable for simple life, but fail to establish the necessary feedback loops for long-term stability. Without these self-regulating systems, environmental conditions would eventually drift beyond the tolerance range for life, ending the evolutionary experiment before complex organisms could emerge. The emergence of multicellular life on Earth occurred only after environmental conditions had remained relatively stable for billions of years. The complexity of modern organisms requires not just suitable conditions, but suitable conditions maintained over enormous timespans. If planetary systems typically fail to maintain habitability for billions of years, complex life would rarely emerge, regardless of how frequently simple life appears initially. Recent research in planetary science supports aspects of the Gaia bottleneck hypothesis. Studies of exoplanets suggest that many factors that contribute to Earth's long-term habitability, such as a sizable moon to stabilize the planet's axial tilt, a magnetic field to protect the atmosphere from solar radiation, and plate tectonics to regulate carbon cycling, may be uncommon among rocky planets in habitable zones. Earth's specific evolutionary history may have further contributed to its unusual stability. The evolution of land plants dramatically accelerated the weathering process, enhancing the planet's temperature regulation. The emergence of organisms that produce calcium carbonate shells created another carbon sequestration mechanism. Without these specific evolutionary innovations, Earth's climate might have been significantly less stable over long time frames. Ironically, the same biological activity that helped stabilize Earth's environment over billions of years may now be destabilizing it through human-driven climate change. This suggests another aspect of the Gaia bottleneck, even on planets that develop initial self-regulating systems. The emergence of technological intelligence might typically disrupt these systems before interstellar capabilities can develop. The Gaia bottleneck hypothesis offers a coherent explanation for why complex life, and particularly technological civilizations, might be exceptionally rare in the universe. If most planets fail to develop or maintain the intricate feedback systems necessary for long-term habitability, then the universe might be filled with worlds where life flickered briefly into existence before environmental conditions shifted beyond survivable parameters. This perspective suggests that Earth's biosphere represents something extraordinarily precious, a rare case where the complex dance between geology, chemistry, and biology created a stable platform for the long, slow development of complex life. The apparent emptiness of our galaxy might reflect not the difficulty of life emerging initially, but the tremendous challenge of maintaining planetary habitability over the billions of years required for intelligence to evolve. The rarity of self-regulating biospheres would help explain why we detect no evidence of other technological civilizations. If complex life is unusual due to planetary instability, then technological civilizations would be rarer still, separated by such vast distances in space and time that communication or detection becomes effectively impossible. We might be detecting no other civilizations because the prerequisites for their evolution are themselves exceptionally uncommon. The Gaia bottleneck suggests a universe where simple life may be relatively common, but complex life remains exceedingly rare. Most planets might harbor microbial life briefly before becoming uninhabitable, their potential for complexity permanently unfulfilled. Earth's remarkable. Sustained habitability might not be the norm, but an extraordinary exception, one that allowed the grand experiment of evolution to continue uninterrupted for billions of years, eventually producing beings capable of contemplating the cosmos itself. The idea that Earth's biosphere represents a cosmic rarity leads us to another intriguing possibility. Perhaps life on our planet didn't evolve independently, but was deliberately planted by an advanced extraterrestrial civilization. This concept, known as directed panspermia, suggests that Earth's life might be the result of cosmic seeding, an intentional spreading of biological material across the galaxy by a technological civilization that existed long before humans evolved. The modern concept of directed panspermia was first formally proposed by molecular biologists Francis Crick, co-discoverer of DNA's structure, and Leslie Orgel in 1973. They suggested that an advanced civilization might have sent microorganisms to Earth in specially designed spacecraft, possibly as part of a broader program to seed life throughout the galaxy. Several motivations might drive a civilization to engage in cosmic seeding. The most straightforward would be a preservation strategy, spreading their biochemistry to other worlds as a backup in case their home planet faced destruction. By seeding multiple planets, they would increase the chances that their particular form of life would survive, even if their civilization did not. This motivation becomes particularly compelling for a species facing extinction due to astronomical threats like their star's evolution or an impending supernova. Alternatively, directed panspermia might represent a form of galactic gardening, a sufficiently advanced civilization might seed life across multiple star systems as a way of transforming otherwise sterile planets into living worlds. This could be preparation for future colonization, a scientific experiment in comparative evolution, or even an aesthetic or ethical project to increase the prevalence of life in an otherwise lifeless galaxy. The technical requirements for such a project would be substantial, but not beyond what we can imagine for an advanced civilization. Microorganisms are remarkably resilient, with some bacterial spores capable of surviving the radiation and vacuum of space for extended periods when properly protected. A purpose-built spacecraft could provide sufficient shielding to protect microbial samples during the interstellar journey, then disperse them when reaching a suitable planet. Intriguingly, certain features of Earth's biology could be interpreted as supporting the directed panspermia hypothesis. The universal nature of the genetic code, with all Earth life using essentially the same DNA system and amino acid structures, might suggest a common origin. While this universality is often explained through evolutionary convergence or a single terrestrial origin, it's also consistent with all Earth life descending from a single introduced sample of engineered microorganisms. Some proponents of the hypothesis point to the rapid appearance of life in Earth's geological record as potential evidence. Current fossil evidence suggests that life appeared on Earth almost as soon as the planet cooled enough to support it, perhaps as early as 4.1 billion years ago. This rapid emergence has sometimes been cited as surprisingly quick if life had to evolve from scratch through random chemical processes. If life was instead introduced from elsewhere, its quick appearance becomes less mysterious. The molecular complexity of even the simplest cells represents another puzzle that directed panspermia might help explain. The leap from prebiotic chemistry to the sophisticated molecular machinery of even the most primitive cells seems extraordinarily complex. If these first organisms were not the result of terrestrial abiogenesis, but were instead the product of directed seeding, perhaps even organisms specifically engineered for their colonizing function, their complexity becomes more understandable. If Earth was indeed seeded by an ancient civilization, we might wonder about their ultimate fate. The fact that they haven't made contact could indicate several possibilities. They might have gone extinct shortly after their seeding project. They might have evolved beyond recognizable forms, or they might be patiently monitoring Earth's development from afar, waiting for humans to reach some developmental milestone before revealing themselves. This last possibility connects directed panspermia to the zoo hypothesis we discussed earlier. Perhaps Earth is being observed by the very civilization that originally seeded life here, a long-term evolutionary experiment or development project that has been running for billions of years. If so, our creators might be waiting for humanity to achieve certain technological or ethical benchmarks before initiating contact. The directed panspermia hypothesis offers an elegant solution to several aspects of the Fermi paradox. If life on Earth originated from another civilization's seeding project, then the biochemical similarity of all terrestrial life makes sense. The apparent absence of other technological civilizations could be explained if the seeding civilization is extinct, transcended, or deliberately maintaining distance while observing our development. Critics of the hypothesis point out that it merely pushes the question of life's origin back one step without resolving it. The seeding civilization itself must have originated somehow. Additionally, while directed panspermia might explain life on Earth, it doesn't necessarily explain the apparent absence of other technological civilizations unless Earth was the only planet successfully seeded. Modern scientific efforts may eventually provide evidence relevant to this hypothesis. As our understanding of astrobiology advances and we develop more sophisticated tools for analysing the molecular basis of life, we might discover signatures of engineering or non-natural selection in the fundamental biochemistry of terrestrial organisms. The specific patterns of genetic code or cellular machinery might contain clues that point toward designed origin rather than natural evolution. The search for biosignatures on other worlds also bears on this hypothesis. If we find that life elsewhere in our solar system shares fundamental biochemistry with Earth life, particularly if found in locations like Mars or Europa, this would strengthen the case for panspermia generally, though not necessarily the directed variety. Conversely, if we discover life with radically different biochemistry, it would suggest multiple independent origins and weaken the case for Earth life being uniquely seeded. While directed panspermia remains a speculative hypothesis, it highlights the possibility that Earth's biological history might be connected to a wider galactic story. Perhaps our planet's remarkable biosphere isn't just a fortunate accident, but part of an ancient, intentional process, a garden planted billions of years ago by beings we might consider, in some sense, our cosmic ancestors. Whether Earth's life emerged naturally or was deliberately seeded, the evolution of human intelligence raises a troubling possibility about our cosmic uniqueness. Perhaps intelligence itself represents not an inevitable pinnacle of evolution, but an evolutionary dead end, a trait that initially provides survival advantages but ultimately leads to self-destruction before interstellar colonization becomes possible. This concept, often called the evolutionary trap of intelligence, suggests that the very cognitive abilities that allow a species to develop advanced technology might inevitably lead to its extinction. From an evolutionary perspective, intelligence evolved not to discover quantum physics or develop space travel, but to solve immediate survival problems. Our ancestors' cognitive abilities helped them find food, avoid predators, cooperate in groups, and adapt to changing environments. The ability to create tools, control fire, and communicate through language provided tremendous adaptive advantages in our evolutionary context. But nothing in this evolutionary history prepared us for the challenges created by our own technological success. The core of this evolutionary trap lies in the mismatch between the pace of technological development and the much slower pace of biological and cultural evolution. Our basic cognitive and emotional architecture evolved over millions of years in small hunter-gatherer groups where threats were immediate and visible, resources were directly connected to survival, and social structures encompassed perhaps 100 individuals at most. Yet within a few thousand years, an evolutionary eye blink, we've created global civilizations with billions of people, developed weapons capable of planetary destruction, and gained the ability to fundamentally alter Earth's climate and ecosystems. This mismatch creates dangerous instabilities. Our threat detection systems evolved to respond strongly to immediate, visible dangers, a predator, a rival group, a poisonous plant, but respond weakly to statistical or long-term threats like climate change or pandemic risk. Our resource management instincts evolved in contexts where consumption was directly tied to immediate survival, not in contexts of abundant consumer goods with hidden environmental costs. Our social instincts evolved for tight-knit tribes, not global political systems with billions of people. The psychological traits that served our ancestors well in their evolutionary context may become actively destructive when combined with advanced technology. Status-seeking behavior that once helped secure mates and resources now drives unsustainable consumption and environmental degradation. Tribal loyalty that once enhanced group survival now manifests as nationalism and warfare with increasingly destructive weapons. Confirmation bias that once helped make quick decisions in dangerous situations now contributes to political polarization and resistance to scientific evidence. Perhaps most dangerously, the very intelligence that allows us to develop advanced technology doesn't automatically provide the wisdom to use that technology safely. We can split the atom before fully understanding the consequences of nuclear weapons. We can alter the climate before developing the political systems needed to address global challenges. We can develop artificial intelligence before ensuring our ability to control it. This pattern suggests a fundamental evolutionary trap. The intelligence required to create advanced technology may be easier to evolve than the wisdom required to manage it. If this pattern is universal rather than unique to humans, it would help explain the Fermi paradox. Perhaps the galaxy is silent because intelligence consistently creates the seeds of its own destruction. Technological species might typically advance to a certain point, develop technologies with existential risks, and then destroy themselves before achieving interstellar capabilities. The silence we observe wouldn't indicate that intelligent life is rare, but that it's consistently self-limiting. The evolutionary psychology supporting this hypothesis appears robust. Many of our most dangerous cognitive biases appear directly connected to evolutionary adaptations. Hyperbolic discounting, our tendency to dramatically undervalue future rewards compared to immediate ones, makes perfect sense in ancestral environments where the future was highly uncertain and immediate survival took priority. This same tendency makes it extraordinarily difficult for our species to make the long-term investments needed for sustainable civilization or interstellar projects. Similarly, our tendency toward in-group favoritism and out-group hostility appears deeply rooted in our evolutionary history as social primates competing for limited resources. This tribalistic tendency created adaptive advantages in ancestral environments but becomes catastrophically dangerous when combined with nuclear weapons, biological agents, or other advanced technologies. If these psychological tendencies are universal features of evolved intelligence rather than human-specific traits, they would create similar challenges for any technological species. The hypothesis suggests a particularly troubling possibility that the development of intelligence beyond a certain point may be actively selected against in evolutionary terms. Species that develop high intelligence might consistently destroy themselves or degrade their environments to the point of extinction, removing their genes from the evolutionary pool over sufficient time. This could create a universe where intelligence consistently emerges, but just as consistently eliminates itself before achieving interstellar capabilities. Some biologists have noted that on Earth, despite billions of years of evolution and millions of species, high intelligence of the human type has evolved only once. This singularity might suggest that such intelligence is not a broadly advantageous trait, but a high-risk evolutionary strategy that rarely appears and seldom persists. Our rarity on Earth might reflect the same dynamics that create apparent rarity in the cosmos. The evolutionary trap hypothesis doesn't require that every intelligent species destroy itself, just that the probability is sufficiently high to make technological civilizations rare on galactic scales. If 99% of technological species destroy themselves before achieving interstellar capabilities, the galaxy could still contain thousands or millions of intelligent species without any becoming visible to us due to the vastness of space and time. If this hypothesis is correct, the silence of the cosmos represents not an opportunity but a warning, a graveyard of species that developed intelligence but not the wisdom to wield the resultant technologies safely. Our own civilization's trajectory, with its accelerating technological power and persistent difficulties in global cooperation and long-term planning, may be following a well-worn path towards self-limitation or self-destruction. Beyond the possibility that intelligence itself might be an evolutionary dead end, we must consider another potential explanation for the cosmic silence. Perhaps there are fundamental technological barriers that no civilization can overcome, regardless of their intelligence or longevity. These insurmountable technological plateaus might permanently limit all civilizations to their home star systems, preventing the emergence of detectable galactic civilizations regardless of how many technological species evolve. The most obvious candidate for such a barrier is the physics of interstellar travel. Our current understanding of physics suggests that faster-than-light travel is impossible, with the speed of light representing an absolute cosmic speed limit. If this limitation proves truly insurmountable, if wormholes, warp drives, and other theoretical FTL concepts remain permanently in the realm of science fiction, then the vast distances between stars create a nearly impenetrable barrier to physical expansion beyond a species' home system. Consider the challenges even for a hypothetical civilization millions of years more advanced than our own. A ship travelling at 99% of light speed would still take more than 4 years to reach the nearest star system. Journeys to stars hundreds or thousands of light years away would take correspondingly longer. The energy requirements for accelerating macroscopic objects to such velocities are enormous, potentially requiring the entire energy output of a star to achieve for larger vessels. If these fundamental physical constraints cannot be circumvented, they would effectively confine even the most advanced civilizations to their local stellar neighborhood. Interstellar colonization might face other insurmountable barriers beyond propulsion. The radiation environment of interstellar space presents extreme challenges for biological organisms, potentially requiring shielding so massive it makes the energy requirements for acceleration even more prohibitive. Micrometeorite impacts at relativistic speeds carry catastrophic destructive potential. These hazards might represent not just engineering challenges but fundamental barriers that cannot be overcome at any technology level. Even if a civilization could technically build interstellar craft, the economics might prove prohibitive. The resources required to build, launch, and sustain an interstellar colony ship might consistently exceed what any civilization would rationally allocate to such a project, especially given the multi-generational timeframes involved. The cost-benefit calculation might simply never favour interstellar colonization over continued development within the home system. Beyond interstellar travel, other technological plateaus might limit civilizations in ways that prevent them from becoming detectable across cosmic distances. Perhaps efficient energy use represents a fundamental direction of technological evolution, with all advanced civilizations naturally minimizing their energy emissions as they develop. This efficiency imperative would make them progressively less detectable from afar, regardless of their actual technological capabilities. Computational constraints might represent another universal plateau. While we often imagine artificial intelligence advancing indefinitely, there may be fundamental limits to computational efficiency or algorithmic capabilities that no technology can overcome. If true artificial general intelligence proves fundamentally impossible due to these constraints, this would limit the potential development trajectories of all technological civilizations. Similarly, there might be fundamental limits to life extension or biological engineering. Perhaps cellular aging, radiation damage, or other biological degradation processes cannot be completely overcome regardless of technological advancement. This would limit the potential lifespan of biological beings and constrain the timescales over which any civilization could operate. The physics of energy production might impose another universal constraint. While we can imagine Dyson spheres capturing the entire energy output of stars, engineering constraints might make such megastructures fundamentally impractical regardless of a civilization's technological level. If capturing and utilizing stellar energy beyond a certain efficiency proves universally impractical, this would limit the energy available to all civilizations and constrain their potential activities. Critically, these plateaus wouldn't require that technological advancement stop entirely, only that it becomes bounded within certain parameters. A civilization might continue developing for millions of years, becoming extraordinarily sophisticated in its science, engineering, and social systems, while still remaining constrained to its home system by fundamental physical or practical limitations. Such civilizations might be numerous throughout the galaxy, yet effectively invisible to each other across interstellar distances. This plateau hypothesis offers a solution to the Fermi paradox that doesn't require intelligent life to be rare or self-destructive. The galaxy might harbour millions of highly advanced civilizations, each thriving within their local stellar systems, but fundamentally unable to expand or communicate across interstellar distances due to insurmountable physical constraints. This perspective suggests a rather melancholy possibility that the silence we observe reflects not our uniqueness or imminent self-destruction, but a universal pattern where intelligent life consistently reaches a level of development where it can contemplate the stars but never reach them. The night sky might be filled with equally isolated civilizations, each wondering about the others but fundamentally unable to bridge the void between them. The most optimistic interpretation of these technological plateaus would be that they represent challenges humanity simply hasn't solved yet, barriers that appear insurmountable from our current perspective, but might yield to sufficiently advanced science and engineering. The history of technology includes many examples of impossible feats that eventually became routine. Perhaps the constraints that appear fundamental to us will prove merely temporary obstacles to future generations. However, if these plateaus truly represent immovable constraints imposed by physics rather than merely engineering challenges, they would establish the permanent contours within which all technological civilizations must operate. The silence of the cosmos might reflect not absence but limitation, a galaxy full of technological species, each confined to their small corner of space by barriers no amount of intelligence or time can overcome. After examining these 20 possible explanations for why we've never discovered intelligent alien life, we're left with a sobering reality. Whether the limiting factor is the rarity of Earth-like conditions, the challenges of biological evolution, the self-destructive tendencies of technological species, or fundamental physical constraints, the evidence increasingly suggests that detectable civilizations might be exceptionally rare in our galaxy. The silent stars above us might reflect not an opportunity missed, but a profound truth about the challenges of evolving, sustaining, and expanding technological civilization in our universe.